Hello everyone, welcome to lab 5. Here we'll talk about fast Fourier transform. In last lab using DFT we found the pulse rate to be 80 bits per minute. Here we use Arduino FFT library to get the pulse rate and verify the results. FFT does the work in n log n, and while DFT does it in n square time complexity. FFT can be implemented using decimation in frequency or decimation in time techniques. So in this code we are using Arduino FFT.h library, and here we are making an object, and these are all the variable initializations. The main part is here FFT.compute, and the keyword here is FFT forward. Here we are computing the forward Fourier transform, not the reverse, that is inverse FFT. So here we are computing FFT forward on V real and V imaginary. As I mentioned in the previous lab that Arduino is not able to handle imaginary numbers, so we have two separate matrices. So here we can obtain the magnitude spectrum and also the k value for which we get the first maximum magnitude spectrum. So this is the spectrum obtained by FFT. Now coming to the results, pulse rate using FFT library with moving average window 5 is 82.03 bpm, and with moving average window 10 is 70.31, which agrees with our TFT results also. Now extracting respiration rate. Raw PPG data contains respiratory information too. While PPG frequency lies between 0.5 to 5 Hz, respiratory frequency lies between 0.05 to 0.5 Hz. Hence FFT can be used to zero out non-respiratory components. That is, if we want only respiratory rate, we'll first perform FFT and we'll set all of the frequencies except these ones to 0 and take inverse FFT. So here is the MATLAB or Octave code. Here we are using the inbuilt FFT function. We are getting my FFT, and after that we are setting my FFT from 17 to its length to 0 and the first to 0. In MATLAB the indexing is from 1, so we have added 1 here. About that, since the frequency lies between 0.05 to 0.5 Hz, that means our KFS by N should be between 0.05 to 0.5 Hz. Now FS is 25 Hz sampling frequency and N is 750. So K should be between 1.5 to 15, that is between 1 to 15. So we have to, in Arduino we have to zero out from 16, and in MATLAB we have to zero out from 17. That's why we have zeroed it from 17. And we are taking inverse FFT, and we are finding the location where we are getting the maximum peak magnitude spectrum. So here is the input signal, here is the frequency spectrum, and here we have zeroed out the rest of the components. We have only some components from 0.05 to 0.5 Hz, and the corresponding signal here, this is the respiratory signal, and the respiratory rate in breaths per minute is 16 bpm. Now for the same implementation in Arduino, we use the inbuilt FFT library. One thing to be noted is that we won't obtain the proper respiratory rate unless we have moving averaged the spectrum also. That is, we have to moving average the signal in frequency domain also, that even with a high window value. After that we'll get the respiratory rate. So this is the extracted respiratory signal, as you can see here, and this is the PPG signal only, that is respiratory components removed. And after that the respiratory rate that we obtain in Arduino is 17.58 breaths per minute, which is pretty much accurate and agrees with our MATLAB results. So that's it for this lab. Thank you.